In this video, I am introducing the topic thermochemistry, and just looking at the topic itself, you can divide the topic into two parts. We have thermo, that is something to do with temperature or heat. Chemistry is chemistry as we know it. So thermochemistry is chemistry that deals with changes in energy, or that deals with heat changes. So we start with the simplest concept that we talk about in thermochemistry, that is energy. So what is this energy? At the top here, we have energy is the capacity to do work or ability to do work. So if you are able to push something, it means you have energy. If you are able to carry something, you have energy. So that ability to do work is called energy. Energy is divided into two major divisions, and the divisions are kinetic energy. Kinetic energy is energy due to motion. And then we have potential energy. This is energy due to position or composition of a substance. Kinetic energy goes further. We have different types of kinetic energies, but one of them is thermal energy. So thermal energy is associated with temperature. As a reminder, what we are dealing with is thermochemistry. So the thermo itself is coming from this term, thermal energy. Here, in terms of potential energy, what we think of is the chemical energy. So the chemical energy as part of potential energy is associated with position of electrons and nuclei in atoms that are found in chemical formulas. So we can see that the thermochemistry has both the potential energy and the kinetic energy, because we are dealing with chemicals that have these potential energies, but we're also talking about the heat that is produced when reactions take place, which is thermal energy. Now let's look at the relationship between the potential and kinetic energy. So we'll see the animation. Maximum potential energy is here because that's the highest position, and here maximum kinetic energy is here. So you see, you observe how the arrow will be moving as the ball is rolling up and down this dip. So you see, as the ball is here, we are at maximum kinetic energy. Whenever the ball is here, we are at maximum potential energy. The same maximum potential energy the other side. So you can see that potential energy can be transformed into kinetic energy, because if the ball is here, it has the highest potential energy. When it starts going down, it is losing that potential energy and goes to the minimum position where potential energy is 0, and then the potential energy starts increasing and the kinetic energy decreases. So there is this interrelationship between potential energy and kinetic energy. Kinetic energy can be transformed into potential energy, and potential energy can also be transformed into kinetic energy. So kinetic versus potential energy. As we already said, this is kinetic energy is energy due to motion of objects. And some examples of kinetic energy, we have thermal energy. Thermal energy is the energy due to the vibration of particles. I mean, that's where we get heat. So the vibration of particles, the translational motion of particles produces a kind of kinetic energy which results into what we call thermal energy. So if you are heating up water, you expect the water particles to be vibrating, to be moving different directions. When you combine all those vibrations and the movement of the water particles, we have thermal energy. So it is related to the heat of an object and the temperature of an object. And then we have radiant energy, which is also part of kinetic energy. Radiant energy is energy kind of from the sun, or energy from radiation. So as we will see later, energy from radiation has speed of electromagnetic radiation, that is the speed of light. So you can see that the energy that is involved here is kinetic. Especially when we talk about the speed of something, it means that thing is in motion. It's the same sound energy. Sound energy, or sound, is as a result of the vibrations of particles, of air particles, and then we can hear from those vibrations. So there is motion in that case. And then we have mechanical energy. It is also part of kinetic energy, because in mechanical energy you have to move something. If you are picking up something, that is part of kinetic energy. That is mechanical energy. In terms of potential energy, we said it's energy due to position of an object, and we have different types of potential energy. So what we need to understand is that potential energy, you are just storing it, you are not using it. Maybe you'll use it tomorrow, or you can use it later on, but the time it's called potential energy, it means it's not doing anything. So we have some examples. Elastic potential. So if you pull an elastic rubber apart, one side and one side, and leave it extended like that, it's not doing any work. But if you drop it, it will come back together. In that case, it changes from the elasticity to motion. But the time that you just stretched it and you're not doing anything, you're just leaving it stretched, it is potential energy. Reason? Because it has a potential to come back to its original position. Then we have gravitational potential energy. So gravitational potential energy is if something is hanging up a tall building. It is very high there, its position is high, it has a lot of potential energy. For you to use that potential energy is you push it, that potential energy changes to kinetic energy. Chemical potential is we have chemical bonds, and these chemical bonds have electrons that store that potential energy. So what happens is, if you have a thing like a peanut has energy, but the energy is not doing anything. It will do something if you eat the peanut, then it will transform into different forms of energy. So the energy found in a peanut or a pecan is potential energy, because it is not doing anything. Electrical potential, if you have not connected the battery doesn't do anything. But we know that it has stored some energy that we can use. Only when you close, when you connect the circuit, the battery will start working. So the battery has potential energy. It can transform that potential energy into other useful forms of energies. So that's the difference between the kinetic and the potential energy. Now, as I already talked about the changes that happen with potential energy, we talk about energy conversion. So if you have a blender, the blender will transform electrical energy into mechanical energy. So we use electricity to be able to crush something. The crushing of something is due to motion, which is mechanical energy. Our bodies convert chemical energy from food into mechanical and electrical energy. A natural gas stove will convert chemical energy from burning into thermal energy used to cook food. So energy conversion is important. That's how we survive. So let's look at these questions. Which of the following is an example of potential energy? So stop the video, think about it a little bit. So for this one, the answer is A. We are saying energy in peanut. That's the only potential energy that we have there, because the peanut will store the energy, and we'll use the energy when we eat it. Then it starts doing other work. In hydroelectric power, the energy from running water is used to produce electricity. What type of energy conversion occurs in this case? Let's think about this one. Stop the video, think about it. So for this one, the answer is D. All of the above. We have potential energy because the water is up the hill, so it has a lot of potential energy there. We have kinetic energy because the water now starts running downhill. And then we have a mechanical energy where we have this turbine. We need to the water gets to the turbine and it turns it round and round. That's the mechanical energy. So we can see that all of the above are involved in the transformation of energy, are involved in hydroelectric power. Now, this energy, the units that we use for energy is the joule, that's the SI unit, and a calorie. So a joule is given as kilogram meter squared over second squared. This came due to the fact that energy is given as force times distance. That's why we have these units. But for now, we are not going to worry much about these units. We'll just worry much about the unit joule. Then we have another unit that we use a lot in the US. It is a calorie, a small c. An important conversion: 1 calorie is equal to 4.184 joule, and 1000 calories is equal to 1 kilocalorie. So a kilocalorie is also known as a food calorie or a nutritional calorie. So if you buy something and you see something written, this food has 5 calories, what it means is that it has 5,000 calories. But now in terms of food, those will be 5 calories, because 1000 calories is equal to 1 kilocalorie, which is equal to 1 nutritional calorie. There is another energy unit that we use in our houses, a kilowatt hour. That's the energy we use in our houses for electricity. So the guys who come to read our meters, what they read is the kilowatt hour. So when we say, all right, this month we have used this amount of electricity, what we are trying to say is that we have used this amount of kilowatt hours. So these are the units, but the units that we will use most are the joules and the calories for this class. Now let's look at the law of conservation of energy. We know that this is one of the fundamental laws of chemistry. Energy is neither created nor destroyed, but however, energy transforms from one form to another. So if you lose energy, don't think the energy has disappeared. No, the energy does not disappear. It just goes into something else, or it just transforms into something else. If we consider a chemical hand warmer, so that's one of the chemical hand warmers that we use in winter, and especially this year, the winter has been really bad. So in the chemical hand warmer, this is ion chemical hand warmer. There is a chemical reaction that takes place. So the ion will react with the oxygen to form iron ferric oxide. So in this case, we are transforming the potential energy that was in this in these chemicals into heat, and we use that heat to warm our bodies. So in this case, the energy is not lost. The energy has transformed from chemical potential to heat, and we have used the heat to warm our bodies. And even in our bodies, there will be transformations of that energy. So the energy is not lost. It is just transformed. So this is the type of transformation that has happened: the chemical energy to thermal energy, and the thermal energy will heat up the hand. And an important law, the law of conservation of mass leads to what we call the first law of thermodynamics. So let's suppose we have a thermos flask here, or we have a calorimeter, something that we can use to burn our peanut or pecan in. So we have a thermos flask here, and we have this container, and we have a peanut here. We burn the peanut. What is going to happen? There will be production of heat here. There will be production of heat here. So the question is, what transformations are going to take place in this case? The peanut will have chemical energy, and as it burns, it is going to produce thermal energy. So we have a chemical from the peanut to thermal due to the heat produced by the burning. So if you assume that this is an ideal thermos flask, we know what an ideal thermos flask is. An ideal thermos flask should not allow heat out, should not allow heat in. That's an important aspect of an ideal thermos flask. So if we assume that this is an ideal thermos flask, and the peanut has 25 kilocalorie energy, how much energy from the peanut will be present 2 hours after the peanut is completely burned? Let's think about this. So we know that the burning of the peanut is losing energy, but the energy cannot get out of the thermos flask because it is insulated. So all the energy lost by the peanut will still be inside the thermos flask. In the end, the total energy in the thermos flask will not change at all. it will remain the same. So after 2 hours, we will still have 25 kilocalories of energy inside the thermos flask, because no energy went out and no energy came in. So, what statement about total energy in the ideal thermos flask can we develop from this observation? We can say that the total energy in the thermos flask, in an ideal thermos flask, is constant, or it does not change, because the thermos flask does not allow energy to get out or come in. Now, if the universe behaves like a thermos flask, what statement can we make about total energy in the universe? We can also say that total energy in the universe is constant. So this is one variation of the first law of thermodynamics. The energy in the universe is not increasing or decreasing. Now let's define a state function and a path function. So let's look at these animations. We have animation, the first one here, the second one. In both cases, we are moving from here. Our starting point is here, our end point is here. So if your grandma or grandfather stays here and he calls you, all right, I want you to come here for Christmas. So you decide, all right, I will use this path all the way to here and I'll get back here. Later on you say, all right, maybe I should use this path all the way to here and I'll get here. So what is important in this case is being able to move from here to here. The path is not important at all. But what is important is being able to move from this starting point to the end point. So in both cases, we are able to get there, but we used different paths. So by definition, if we now think about it in terms of potential energy due to position, we see that in both cases, change in potential energy is given by this. Just a distance from here to here. That is, no matter the path, the potential energy change is the same. So we can conclude that potential energy is a state function. But what is the definition of a state function? A state function is a function that depends only on initial and final state of the system, regardless of the path taken. So it doesn't matter even if you go all the way here and come back here. It doesn't matter. What matters is the distance from here to here, or from here to here, or from here to here. That's what state function is about. And because of that, we can use this, the delta E, to give us the change in that state function, or the change in that function, as we'll see later what I mean by that. Another example that we can use to show the difference between a state function and a path function. So a path function depends on the path taken, while the state function depends only on the initial and final state of the system. So let's look at these two systems. Compare the amounts of heat needed for the temperature between A and B if the same type of hot plate is used. You can see in A, there is not much water. In B, there is a lot of water. So our aim is to heat up the water from 23 degrees Celsius to 89 degrees Celsius in both cases. Which one between A and B do you think will take a lot of time to heat up? Definitely B will take a lot of time. A will take less time to heat because there is less water. So you can see that in terms of the heat, we need more heat here. We need less heat here to make the same change in temperature. In other words, the heating will depend on how much time you have heated. Like here, you need to heat, if you are using the same hot plate, you need maybe 10 minutes to heat this one. You may need 30 minutes to heat this one. So the amount of heat that you are giving will depend on the path that you have taken, will depend on the hot plate that you have used. But your aim in both cases is to move from the initial state of 23 degrees Celsius to the final state of 89 degrees Celsius. In both cases, it doesn't matter how you heat up the system. So how you heat up the system is a path function. So we see that the bigger container will need more heat based on the mass. The smaller container will need less heat. In this case, we can say temperature is a state function and heat is a path function. We have used different amounts of heat here, but the change in temperature is the same. The different amounts of heat that we have used are the path to give us that change in temperature. But the change in temperature itself is a state function. Now, let us define something that we call internal energy. Internal energy is also a state function. By definition, internal energy of a system is the sum of kinetic energy and potential energies of all the particles that compose the system. So for example, if you have a bucket of water and you put a thermometer in there, you see that if it's during warm times, the thermometer will be maybe at 60 something Fahrenheit. In cold temperatures, maybe the thermometer will be at something like 50 Fahrenheit or so. So what you are measuring that time is the thermometer just gives you an idea of what the internal energy of the system at that time is. So the sum of the kinetic energy and the potential energies of the particles that compose the system are internal energy of the system. And internal energy is a state function. It depends only on the initial initial state and final state. So one thing that we need to know about internal energy, we can give the change in internal energy. This is known as delta. Delta is a symbol for change. So the change in internal energy can be given as the final internal energy minus initial internal energy. What do we mean? Let's say we have this reaction, carbon and oxygen to form carbon dioxide. So the reactants will have their internal energy, and the products will also have their internal energy. So in terms of this reaction, we'll say up here we have the reactants, down here we have the products. To move from these reactants to form these products, we lose that internal energy, and it's given as delta E. So the change in internal energy will take the reactants to become products. So in this case, this coordinate here is the coordinate showing that we have internal energy here for this reaction, and the arrow going down is showing that we are actually losing the internal energy. The products have lower internal energy than the reactants. So what it means is that carbon has its own internal energy, oxygen has its own internal energy. When they combine, they'll lose that internal energy, and they will have carbon dioxide, which is at lower internal energy, and that can be given by delta E. So for chemical reactions, delta E is the difference in internal energy between reactants and products. So let's go back to looking at the heat exchange in a thermos flask and make some definitions. A system and surrounding. So the system is the part of the universe that we are studying, while the surroundings are the rest of the universe that interact with the system. So if we look at this one, in this diagram that we see this side, what is our system and what is our surrounding? So in this case, the burning peanut is the system, but the vessel and everything in it are the surrounding. So what it means, the vessel, water, and air in the flask are the surroundings. So whenever we have a system, what we are interested in, there is always the surroundings. In terms of energy, if the peanut loses 25 kilocalories of energy, the surroundings will gain the same amount of energy, because energy is neither created nor lost. If it is lost in one system, it should be gained by another system. A thermos flask, there is no energy going in, no energy coming out. So we can call it an isolated system. So for an isolated system where no exchange of energy and mass with the environment occur, that is an isolated system, internal energy is constant. So the internal energy of this system, the system is not going to change. It will just remain the same. Especially if we now consider this whole thermos flask as our test subject. The internal energy lost by this will be gained by the rest of the thermos flask, and there will be no energy lost and no energy from the outside getting in. So internal energy is constant. This is the actual first law of thermodynamics. For an isolated system, internal energy is constant. Or we can say change in internal energy is zero, which means internal energy does not change. It is constant. So let's look at the change in internal energy of the flask. We are saying because we have isolated flask, this flask is an isolated system, the change in internal energy of the flask will be equal to the change in internal energy of the nut here, the peanut, plus the change in internal energy of the surrounding within the flask. But because we are saying the change in internal energy here is constant, or the change in internal energy is zero, the change in internal energy of the flask is equal to zero. Because an isolated system, internal energy is constant. So we can ignore the flask and say change in internal energy is equal to energy of the system, if the peanut is our system, plus energy of surrounding is equal to zero. So this is equal to zero. This means that the energy of the system is equal to the negative energy of the surrounding. This is a simple thing. What it means is, if the system loses energy, the surrounding is going to gain the energy. That's why the system is positive and the surrounding is negative. If the surrounding is negative, the system is positive. So we need to take note that all right, if the peanut is losing energy, will the water be warm or cold? So if the peanut is losing energy, the water will become hot. So the peanut loses energy, the water gains energy. That's what it means. So this equation is important. Delta E system is equal to negative delta E surrounding. So let's answer this question. Which statement is true of the internal energy of a system and its surrounding during an energy exchange with negative delta E system? So here we say delta E system is equal to negative AE surrounding. But what if the opposite happens? Think about these answers. You can stop the video and think about the answers. In this case, the internal energy of the system decreases and the internal energy of the surrounding increases. Because if one is positive, the other should be negative. So we need to take note of this, and we need to take note of this question specifically. So I'll just go quickly through the energy processes. Let's define work. Work is done when force applied to an object moves that object. Work has units of joules, but it's not actual energy, it's just a process. The same heat. Heat is when energy transfers due to differences in temperature. Heat has units of joules, but it's also just a process. So a system will normally exchange energy with the surrounding through two processes: work and heat. In other ways, just a reminder, a system normally exchanges energy with the surrounding through work and heat. So we can say change in internal energy is given as Q plus W, where Q is heat, W is work. This is what we call the mathematical statement of the first law of thermodynamics. So let's take note of this. It's very, very important. Delta E is equal to Q plus W. That's the mathematical statement of the first law of thermodynamics. Heat and work are path functions, but when you add them, they give a state function, which is delta E. So you need to take note that we have not written here delta Q or delta W, but we have written delta E here. It's only the state function that have the delta. The path functions do not have delta on them. Lastly, I just want us to think about work and heat. Work done on the system is always positive. Work done by the system is always negative. So what do I mean by work done on the system? If a gas expands, or if I have a balloon and I squeeze the balloon, I'm doing work on the balloon. So the work in that case is positive if the balloon is the system. But now if the balloon, when I squeeze it, the balloon pushes me back, the balloon is doing work on me. In that case, work is negative. In terms of heat, heat absorbed by the system is positive, while heat released by the system is negative. So positive heat is known as the reaction that absorbs heat is known as endothermic, that we'll see later. The reaction that releases heat is known as exothermic. So please make sure to answer the questions that go with this video, and be prepared for class. We may just quickly answer some questions on what we have discussed in this video and then proceed. Thank you.